Assalamu alaikum students. Our learning objectives are calculate the number of phases in Eutectic phase diagram, calculate the degrees of freedom in phase diagram, what is iron carbide diagram, what is the effect of composition in temperature on allying elements, and what is the effect of composition on and temperature on mechanical properties. But before we discuss this, we will continue with our previous lecture in which we were discussing the eutectic phase diagram, and we were discussing about the lead tin system, the microstructure of the lead tin with different composition. And in this lecture, we will also study the effect of mechanical properties due to the change in composition and due to the change in the temperature. For this, we will study the microstructure development as well. Here we will discuss the development of the fourth case of the development of microstructure for the lead tin system. The Li is cooled down from a temperature of 300, and the point of interest is 40% by weight of 10, and the result when it is cooled down from 300 degrees centigrade until the eutectic invariant temperature, the isotherm line is crossed, and below that the resultant microstructure is the alpha phase particles in the eutectic microconstituents, the eutectic microconstituents, which is a new type of grain particles. In point N, point M, which is just below the isotherm temperature, the primary alpha in the eutectic structure, there are two microconstituents, namely primary alpha and the eutectic structure. The primary alpha is the round grain size, and the eutectic structure is the subsequent phases, layers, the rectangular layers. One is the blue, the other is the pink. These layers is the retraction, but with the primary constituents, primary alpha constituents. The eutectic mixed structure microconstituent is a microconstituent, even though it is a mixture of two phases, because it has distinct lamellar structure with a fixed ratio of the two phases. It is possible to compute the relative amounts of both eutectic and primary alpha microconstituents. Because the eutectic microconstituents always forms from the liquid having eutectic composition, this microconstituent may be assumed to have a composition of 61.9% by weight of 10. The rest is same, like when the alloy is cooled down from a temperature of 300 degrees centigrade, the microstructure is liquid, and then when the liquidus line is crossed, the solidification starts. Small grain alpha particles begins to form at point K. Once the after sufficient amount time is given for the cooling, the microstructure of alpha begins to form stronger, which are surrounded by the liquid particle until the isotherm point is crossed at point M. These primary alpha particles are surrounded by a eutectic mixture and without liquid particles. So these eutectic microconstituents are formed, but from where they occur, they may be with the composition. There must be the effect of the composition. The effect of the composition is like 61.9% by weight of 10 have the effect on the microconstituent. Want to explain the microconstituent a bit more. When for the previous case, just like in case number 4, conditions of equilibrium are not maintained while passing through the alpha, beta, and liquid phase. The uh, the following consequences will be realized for the microstructure upon crossing the eutectic isotherm. Number one, the grains of the primary micro constituents will be cored. That is, have a uniform, non-uniform distribution of the solute across the grains, and the fraction of the eutectic microconstituent will be formed will be greater than the equilibrium situation. Just like in our case, the example, the eutectic microconstituent formed, or the size is greater than the microconstituent. Gibbs phase rule. In Gibbs phase rule, it provides us when we use this rule, it is a criteria that determines how many phases can coexist within a system at equilibrium. So, phase diagram and phase equilibrium are subject to the laws of thermodynamics, but how to determine the number of degrees of freedom, or how many variables can be used, or we can come to know after using the Gibbs phase rule. P, this is the Gibbs phase rule. P plus F is equal to C plus N. P is the number of phases present, F is the degrees of freedom, temperature, pressure, and composition. C is the components or compounds. N is the non-compositional variables. For example, for the copper silver system at 1 atmospheric pressure, for a single phase P, N is equal to 1, which is a temperature. N is the non-compositional variables. Non-compositional variable is temperature, which is 1. C is the components or compounds. 2 components, copper and silver, are used. P is for the single phase, single alpha, beta, and liquid are single phase. Then F will be equal to 2, putting the values in this equation. 2 plus 1 minus 1 is equal to 2. So 2, this means that to characterize the Li within a single phase field, 2 parameters must be given: temperature and composition. If 2 phases coexist, for example, alpha plus L, beta plus L, alpha plus beta, then according to the Gibbs phase rule, we have 1 degree of freedom, which F is equal to 2 plus 1 minus 2, which is 1. So if we have temperature or composition, then we can completely define the system. If 3 phases exist for the binary system, there are 0 degrees of freedom. This means that the composition and temperature are fixed. This condition is met for a eutectic system by the eutectic isotherm. The iron-iron carbide system. The metal iron is a primary constituent of some of the most important engineering alloys. Iron in pure form is called ingot iron. It is used for drainage culverts, roofing, ducts, stores, washing machines, etc. A typical analysis for iron in ingot iron is carbon by weight is 0.012%, manganese is 0.17%, phosphorus is 0.05%, sulfur is 0.025%, while there can be some traces of silicon can also be found in the composition of ingot iron. I repeat, Ingot iron is the pure form of iron. Mechanical properties. Typical mechanical properties of ingot iron are: tensile strength is 40,000 psi, elongation in 2 inches 40%, Rockwell Brenel hardness is 30. Iron is an allotropic metal, which means that it can exist more than one type of lattice structure depending upon the temperature. Cooling curve of pure iron. This is the cooling curve of pure iron. This is important to explain because iron is the main constituent of iron carbide diagram. So we must know about the latest structure of iron at different temperature when it is cooled down from its melting point to the lowest the latest structure. The melting point of iron is 2802 degree Fahrenheit. At this temperature the iron is in liquid form. Upon cooling the iron from melting state, the iron solidifies below this temperature, and the atoms are rearranged with each other, and the melting form is converted to delta iron body center cube. And after that, after further cooling, after 2554 degree Fahrenheit, the delta iron BCC is converted to gamma iron FCC face center cube non-magnetic. And when the temperature reaches to 1666 degree Fahrenheit, another phase change occurs from FCC non-magnetic gamma becomes magnetic without a change in lattice structure. Means over here it's 1666 degree Fahrenheit, the iron is the lattice structure is BCC, while below 1414 degree Fahrenheit iron is still BCC. The structure is magnetic. The only difference between these two lattice structure is the same, but the property is changed. One is between the range of 1414 degree Fahrenheit and 1666 degree Fahrenheit, the iron behaves as non-magnetic, while below 1414 degree Fahrenheit the iron is the iron carbide diagram. The temperature at which the allotropic changes takes place in iron is influenced by alloying elements, the important of which is carbon. What are the allotropic changes? We know that allotrope are the different structural forms of the same element and exhibit quite different physical properties and chemical behavior. Like we discussed in the previous slide, that when an iron is cooled down from the 16 degree Fahrenheit to 14 degree Fahrenheit, the lattice structure becomes is similar, but the physical properties of iron is changed from non-magnetic to magnetic form. So allotropes are different structural forms of the same element but exhibit quite different physical properties and chemical behaviors. All the allotropic changes give off heat when iron is cooled and absorb heat in endothermic reaction when it is heated. So this is the part between pure iron and interstitial compound iron carbide containing 6.67% carbon by weight. Therefore, Iron carbide diagram is actually a map of the temperature at which different phase different phase changes occur on very slow heating and cooling in relation to carbon is called iron carbide diagram. It shows the type of alloys formed under very slow cooling. We do proper heat treatment temperature, and we will study how the properties of steel and cast iron can be radically changed by heat treatment. Before we go to iron carbide diagram, we must discuss the various phases that appear on the iron carbide diagram. So the various phases that appear on iron carbide diagram are ferrite, pearlite, austenite, cementite, ledeburite, martensite. Ferrite and pearlite. Ferrite is known as alpha solid solution. It is an interstitial solid solution of small amount of carbon dissolved in alpha BCC iron. This is the ferrite. This region is called a ferrite, the alpha solid solution. It is a stable form of iron below 912 degree centigrade. The maximum solubility is 0.0225% carbon at 723 degree centigrade, and it dissolves only 0.08% carbon at room temperature. It is the softest structure that appears on the diagram. What is pearlite? Pearlite is Eutectoid mixture containing 0.8% carbon and is formed at 723 degrees centigrade on very slow cooling. Pearlite is formed at 723 degrees centigrade, while the maximum solubility at 723 degrees centigrade, the ferrite structure is formed. When the carbon percentage is 0.025%, and at 723 degrees centigrade, the ferrite dissolves only 0.08% at room temperature. So the dark regions in this structure, this is one dark region, this is the other dark region. These are the pearlite. This is the microstructure of alpha ferrite and pearlite. P is for pearlite while alpha is shown for the ferrite. What is austenite? Austenite is an interstitial solid solution of carbon dissolved in gamma FCC iron. Maximum solubility is 2% carbon at 1130 degrees centigrade, which is quite higher than pearlite and ferrite. High formability. Most of the heat treatment begin this single phase. It's normally not stable at room temperature, but under certain conditions it is possible to obtain austenite at room temperature. Attached is the microstructure of austenite. Cementite and Ledeburite. Cementite or iron carbide is very hard and brittle and intermetallic compound of iron and carbon. Iron and carbon is iron carbide contains 6.67% carbon. It is a hard structure that appears on the diagram. It has low tensile strength, approximately 5000 psi, but high compressive strength. Ledeburite is the eutectic mixture of austenite and cementite. It contains 4.3% carbon and formed at 1130 degrees centigrade. In this figure, the white region is called ferrite while the dark region is a cementite. Martensite. It is Martensite. It is a supersaturated solution of carbon and ferrite. It is formed when steel is cooled so rapidly that the changes from austenite to pearlite is suppressed. Actually, martensite is a body-centered tetragonal form of iron in which some carbon is dissolved. Martensite forms during quenching when the face-centered cubic lattice of austenite is distorted into the body-centered tetragonal structure without the loss of its contained carbon atoms into cementite and ferrite. Simply, it is a BCC tetragonal form of the iron in which some carbon is dissolved. It forms during quenching process. Microstructure of different phases of steel are now shown in this diagram. If we look at the mild steel, the microstructure of this mild steel, it's a single phase, and all the alpha particles, the solid grain alpha particles, are formed without any liquid or any impurities are present in these fine grain boundaries. The grain size and grain shape is look like solid boundaries without any liquid or any other impurities. That's why we call it a single phase. For a dual phase steel, it's a type of a two phase region. We can see some grain at the outer grain boundaries. We can see some dark points around the alpha, surrounded by the alpha grain size. So that's why we can call it uh, two phase. The second phase, the one phase is alpha ferrite, while the second phase is martensite. So the other two phase example is duplex steel. The alpha particles are surrounded by gamma particles. Some impurities of gamma, like 50% alpha and 50% gamma size, can be seen in this microstructure. That gamma is, we call it austenite. So that's the example for the duplex steel. For the multi-phase TRIPS steel, we can see in the microstructure, we can see different types of grains. One is alpha particles, so in the other are dark regions. The third one is small other impurities. We can call it retained austenite gamma. Retained austenite, and alpha B is benite, alpha is ferrite. So when more than two phases are present in the microstructure, we can call it multi-phase. So trap steel is the example for the multi-stage, multi-phase. Tensile properties of unalloyed and nickel wrought iron. In this table, we come to know that why the alloy of iron is important. So there is a comparative study between the unalloyed wrought iron and nickel wrought iron. the unalloyed, the mechanical properties of wrought iron is improved when another element of nickel is melted with the wrought iron with some composition of the nickel. The mechanical properties, the tensile strength is improved from 48,000 to 60,000 psi. Similarly, the yield point is also improved. The elongation is also reduced from 25 to 22% in 8 inch, and reduction in area is from 45% to reduced from. Various features of iron carbide diagram. This is the iron carbide diagram, which is most important diagram. We will explain this iron carbide diagram with respect to different phases and with respect to different reactions, with respect to different regions, and with respect to different compositions of carbon and different alloys which we will get after different composition of carbon at different temperatures. The phases which are present are the liquid region, which is delta BCC structure. Delta BCC structure is between the line is between that temperature range between 2802 degree Fahrenheit in 2500 degree 54. Delta region. This one is the delta region. Alpha ferrite, which is BCC structure, ferromagnetic, fairly ductile structure. The alpha region is between the range of temperature 1666 below 1666 degree Fahrenheit is the alpha ferrite BCC structure. This one is the alpha region, and gamma region is between the range of 2554 degree Fahrenheit to 1666 degree Fahrenheit. This is the gamma austenite region, which is FCC structure and non-magnetic and ductile. This is the phase, the liquid phase. The other phase is the liquid plus delta region, liquid plus gamma region, and liquid plus the iron carbide region between E and D, and C and E line represent the gamma plus liquid region. Some parts of liquid and some solid crystals are formed within this region. Similarly, the pure solid solution is gamma plus alpha region, and the three horizontal lines, one is the small line, this small line is the other one is the line C to E and E to D. The third line is between the line the line H and K. These represents the isothermal reactions. The maximum solubility of carbon in ferrite is 0.022%. Maximum solubility of carbon in austenite region is 2.11%. The small portion of the diagram in the upper left corner is known as the delta region. This one is the delta region. We will explain this further. We will zoom this small region, and we will explain the different reactions which are taken place. This region is known as the delta region because of the delta solid solution. So we must recognize the horizontal line at 2702 degree Fahrenheit, 2720
2720 degree Fahrenheit, which is the small line. This one small horizontal line. The reaction taken place at 2720 degree Fahrenheit. This reaction is called peritectic reaction. The equation for the peritectic reaction is when the liquid is mixed with the delta solid solution. After cooling, we can get austenite, or if we sorry, after heating we will get the austenite, or if we cool down, we may get the liquid plus delta region, the liquid plus delta region, which is this one. So the austenite reaction, this reaction is called a peritectic reaction. This one is the peritectic reaction. Liquid plus L, liquid plus delta, we may, after when we heat it or when we cool this down, we will get austenite. Austenite, we will get the austenite, and that austenite is represented by the gamma solid solution, and that gamma is
We want to explain iron carbide diagram a little more. Carbon is an interstitial impurity in iron. It forms a solid solution of alpha, gamma, and delta phases of iron. The maximum solubility in BCC alpha ferrite is limited. Maximum solubility is 0.022% weight percent at 727 degrees centigrade. BCC has relatively small interstitial positions. Maximum solubility in FCC austenite is 2.14 by weight percent at 1147 degrees centigrade. FCC has larger interstitial positions. Mechanical properties. Cementite is very hard and brittle, can strengthen steels. Mechanical properties also depends on the microstructure, that is how ferrite and cementite are mixed. Magnetic properties. Alpha ferrite is magnetic below 766 degrees centigrade. Austenite is non-magnetic. The classifications: three types of ferrous alloys: iron, steel, cast iron. These are three types of ferrous alloy. The classification is based on the percentage of carbon. Less than 0.008 weight percent in carbon in alpha ferrite at room temperature, 0.008 to 2.14 by weight percent of carbon, usually less than 1% by weight, is alpha ferrite plus iron carbide at room temperature. The cast iron, the classification is for the cast iron is between 2.14 to 6.7 by weight percent, usually less than 4.5 by weight percent for the cast iron.
three phase reactions. We have already discussed the three horizontal lines. These three horizontal lines represent the three different phase reactions, and the regions are one is the small region, which is called delta region, the small region. This delta region is we have represented this in the previous slide. This is the delta region. This is one phase reaction. The other second phase reaction is this one between the line C to E and E to D. The third horizontal line is between is the line H to J and J to K. These are the three phase reaction. They are different with respect to different compositions of carbon. Peritectic reaction occurs at 0.1% carbon and at a temperature of 1495 degrees centigrade. The delta iron, when delta iron is added with the liquid iron solution, gamma austenite is formed. This is one phase reaction. The gamma austenite, the austenite region. The second phase reaction is the Eutectic reaction, which is at 1147 degrees centigrade. This reaction occurs at 1147 degrees centigrade. And the third one is the Cementite reaction, when the liquid iron is dissolved into gamma iron plus iron carbide cementite, which we can also call Ledeburite. So the alloys at this region are called cast iron. The Eutectoid reaction occurred at 727 degrees centigrade at a composition of 0.77% carbon. The gamma iron.
There are different types of reactions occurs at a single point. We call it three-phase reactions. The different types are eutectic, eutectoid, peritectic, peritectoid, monotectic, miscibility, GIBBS, oil and water region, where two liquid phases coexist. The three-phase reaction occurs. The eutectic reaction occurs. The equation for the eutectic reaction is for the solid phase. For the liquid phase, liquid is transformed into two solids. Eutectic point. In this figure, eutectic point, the liquid phase is transformed upon cooling. It is directly transformed. Once the isothermal temperature line is crossed, the liquid is transformed into two solids. So this is the eutectic point. What will be the practical example of this eutectic reaction? Students need to find out, because in the last slide presentation it is being discussed. Eutectide. In eutectide reaction, one solid is transformed into another two solids. The eutectoid. This is the example in which gamma solid is transformed into alpha plus beta two other solids. Eutectoid reaction. Peritectic reaction, in which one liquid plus solid is mixed to form another solid. One liquid plus solid is formed to form another solid. One liquid plus solid is formed to form another solid, which is beta. This is peritectic reaction. And peritectoid. Peritectoid reaction. In peritectoid reaction, two solids mixed with each other and form another solid. This one, two solids mixed with each other form another solid, S1 plus S2. Here two solids alpha plus gamma forms mix after cooling and after crossing the eutectic temperature. Peritectide reaction occurs, in which two solids forms another. Monotectic reaction, in which a liquid is transformed into solid plus another liquid. Monotectic reaction. This is a unique reaction in which one liquid after passing to the isothermal temperature, in all these diagram, when they are cooled or either heated, after heating or after cooling, they transform after passing through that point, the common point, the three-phase point, another the eutectic reaction occurs. So here for the monotectic reaction, when the substance is cooled down and they are passed to isotherm temperature, another solid and another liquid is formed. Eutectoid and peritectic reactions. Eutectic point. Eutectic is reaction. Eutectic reaction occurs when the liquid transforms to two solid phases. The reaction is liquid. By cooling, we can get alpha plus beta, two solids, or if they are heated, it transforms into liquid. The example is in the lead tin system at 183 degrees centigrade at a composition of 61.9% by weight of tin. This reaction takes place. Eutectoid. Eutectoid reaction takes place when one solid phase transforms to two other solid phases. The reaction is the schematic reaction is this one solid transforms to solid 2, solid 1 transform to solid 2 and solid 3. The practical reaction can be written is the gamma by cooling will be transformed to alpha plus iron carbide, or when the alpha particles plus iron carbide are heated, we can get back the solid one. When these two solids are combined and they heated, or when this solid is cooled down, two another solids are formed. The example is for iron in carbide, it's 727 degrees centigrade and at a percentage of 0.676 weight percent carbon, this reaction occurs. Peritectic reaction. Reaction occurs when the liquid and one solid phase transform to second solid phase. Liquid plus solid transform into second solid phase. Peritectic. Delta. The example is when delta iron is mixed with the liquid iron, pure iron. When it is cooled, we can get another solid. For copper zinc phase diagram at a temperature of 598 degrees centigrade and 778.6% weight of zinc, we can get another solid. So this is a review of the eutectic, eutectoid and peritectic reactions which are occurred, and some examples are also mentioned for the more explanation. Development of microstructure in iron carbide alloys. The first iron carbide, we will start with the minimum percentage of carbon content, which is microstructure of eutectide steel. In the given figure, the given plot is the schematic representation of microstructure of an iron carbide alloy of eutectide composition with 0.76% weight of carbon. We consider in this discussion, we consider the slow cooling in which equilibrium is maintained. The eutectide reaction takes place at carbon percentage of 0.76% and at a temperature of 727 degrees centigrade. The eutectide reaction is this one, in which the austenite is formed into alpha another solid
into austenite is formed into two solids. So one is iron carbide, the other is alpha ferrite, with the carbon content of 0.022% by weight. So the microstructure depends upon the carbon content and heat treatment. The carbon content is 0.7%, heat treatment it is very slow cooled. Consider this Li is initially at 800 degrees centigrade. Our point of discussion is this line x to x prime, which is the known carbon content of 0.7%, and Eutectoid reaction takes place. Initially our Li is at 800 degrees centigrade, that is beginning at the point in A. Initially this Li, if we look at the microstructure, this Li is composed entirely of austenite phase, having a composition of 0.76% by weight of carbon, and this is the corresponding microstructure, austenite structure. All the grains are austenite. This structure will remain the same until we cross the isothermal temperature, which is 727 degrees centigrade. But as soon this temperature point this point is crossed, the austenite region begins to composed into the alpha ferrite particle and iron carbide. If we look at the microstructure at point B, as soon we reach to the point B, we have cooled down from the 800 degrees centigrade and maintain the same composition to we have cooled down this Li from 800 to 700, below 727 degrees centigrade, and at 727 degrees centigrade the reaction occurred. According to this reaction, according to the microstructure, we can see the lamellae structure of alpha, which is surrounded by the iron carbide structure. So this is the formation for alpha and iron carbide structure, the decomposition of the austenite structure. The microstructure of Eutectoid steel is terms is Pearlite, which is shown at by point B. The austenite is decomposed into alpha Pearlite and iron carbide at this line XX. So this is the Pearlite. We see the alternating layers of Pearlite and iron carbide regions. We call it a lamellar structure. The Pearlite exists as grains. The photomicrograph of the Eutectoid steel showing the Pearlite microstructure consisting of alternating layers of ferrite, which is the light phase, alternating light phase, and the iron carbide, the thin layers, most of which appear the dark. The iron carbide layers appear dark. So the thick light layers are ferrite phase, and the cementite phase appears is thin lamellar structure, most of which appear dark. The many cementite layers are so thin that the adjacent phase boundaries are so close together that they are indistinguishable at this magnification, and therefore it appears dark. Mechanically, if we discuss about the mechanical properties, mechanically Pearlite has properties intermediate between the soft ductile ferrite and hard brittle cementite.